We have learned the use of concept infinity in calculus. If you didn't see the calculus video, please go back and check it out. Okay, to get the integral of something, we need to add infinite number of times the infinitesimally small number. Okay, so when we slice the 1/4 circle into the pie shape, and we figure out how to get the area, so the operation we performed was an infinite number of times. Okay, but you have to be careful when you use infinite numbers. It has to be mathematically accurate, because there are a lot of fallacy that can fool you. For example, here, suppose path A is A, C, B, and the path B is A to B direct. Okay, it's obvious that A, C, B is a longer path than direct path A, B. So we are going to go through this or this. Now we can prove that the path A is same as path B. How do we do that? Watch carefully. Okay, suppose we have A to C and we take a midpoint, and C to B we take a midpoint. Okay, and we fold this portion here below. Okay, so this path is same as this path. Am I right? Okay, now we do same thing. Take a midpoint and we fold this part down here. We do same thing here. Okay, so this path is same as this path, and that is same as this path. Okay, we repeat that infinite times. Eventually what's happening is the path will be almost same as direct path A and B. Therefore, the path A is same as path B. What's wrong with that? I mean, we proved it, right? Did we? Well, how do you break this fallacy of infinity? Okay, infinite operation, the line become almost same. Path A and path B, they become almost same. So what's wrong with that? Well, what's wrong is, say we have a equilateral triangle here. That means AC and CB and ABs are all same. Okay, so we have this path A has twice as long as path B, right? Okay, when we do this trick, folding this part down, then what is the ratio between path A and path B? 2, still same. Okay, we fold it again and again. How many times you do, no matter how many times you do, the ratio of the length is 2. So important thing is to keep the ratio for the operation infinity. So the answer is, no matter how many times you do, this zigzag line has twice as long as straight line A to B. That's the correct argument. Okay, now we can do something similar to this. Okay, we can make the same argument using a different geometry. Here we have this path versus this path, saying A to B. Okay, this path, if this is R, then this is 2R. So this path will be 2R pi, well, 4R pi and a half. So it's gonna be 4R pi half 2R pi, right? Okay, how about this path? This is gonna be pi r, and this is pi r, so it's going to be 2r pi. So this path and this path has the same length. Okay, we do same thing again and again and again, keep doing it. So this path become eventually straight line from A to B. Okay, but the ratio is 2 pi r. From here to here is 4r. So 2 pi r 4r will be pi over 2. That's the ratio. This ratio stays same no matter how how many times you repeat operation. So that's how you break this fallacy. It sounds like this path become completely same as this path, same length after infinite times of operation, but it's not, because the ratio is always same. Okay, so here's a question. Well, at some point some student asked this kind of question to math teacher. The area, what is area? Maybe area is infinite number of line collected. That makes area. So if this is H, the line segment, and it's collected for number of lengths L, the area will be H times L. What's wrong with this? You can have an infinite number of lines, because even that thin, if you have an infinite number, it may cover this entire area. Is that correct? No, the math has to be very accurate, very precise. Okay, the definition of line in the math has zero width. Okay, it's not infinitesimal small number, zero. So no matter how many times you add the zero, it's zero. So even you put so many lines here, it won't cover. So area is something totally different from the collection of line. Okay, this is the correct way to explain what the area is. Here's a funny question somebody may ask. Suppose we have a 2-inch diameter hole, okay, and you try to fit 2-inch round bar into this hole. Can you fit? Well, if you ask a mathematician, they are very precise. They say, sure, it's fit. 2-inch hole, 2-inch diameter bar, it should get in. Okay, that's a mathematician. But if you ask a physics professor, he said, no. there is so-called friction between hole and bar. So if it's exactly same size, friction is so large, it won't fit. Okay? But you ask engineer, does it fit? Well, engineer said, maybe, most likely it's fit. What do you mean, maybe, most likely? Well, engineer said, well, you know, if you hit it with a hammer, it will fit. Okay? So, that's a 3 different answer you get. As long as you do the math, you have to be very precise. Okay? So answer for this, as a mathematician, it will fit. Okay?